So far we have been looking at why radiative corrections. No, we have looked at radiative corrections and so on. So the renormalization of the standard model and everything. So now you may ask the question as why radiative corrections. We started okay. So we started looking at renormalization of standard model and the procedure and everything. So, but what do you really do? Do you really need these radiative corrections or not? So we said, I said in the experiment we need it, okay, because experiment is measuring very precisely. But just to give an idea, how much is the difference when you calculate things without radiative corrections and with radiative corrections? Experimental measurements I showed you last time in the PDF file, everything essentially. So for example, if you just take numbers of mw square sin square theta w and everything and calculate 3 level numbers of standard model, okay. 3 level number means without radiative correction. So suppose if I just use these inputs, so then we have the inputs like alpha is equal to 1 by 137. Let's use the most precise value, essentially 3604 with the error bar of 1, and GF has a measurement 1.166344 with the error bar of 11 into 10 power minus 5 GeV or minus 2, and then sin square theta w is equal to 0.231 plus minus 0.0006. This is coming from neutrino scattering. So I take the alpha but measured at atomic scale, MeV scale essentially. I am not saying that there is a running alpha or something, okay. Whatever it, what we don't care about the scale essentially. I am not saying it's all 3 level numbers. What is the GF from nuclear physics experiments and what is the sin square theta w. Now put these numbers and calculate MW and MZ, okay. Put these numbers and calculate MW and MZ. Do you know what is MW square sin square theta w by alpha by root 2 GF. So from this you can get MW square and you can also get mg square, and the theory numbers, 3 level numbers are MW is equal to 77.6 plus minus 1.0 GeV, mz is equal to 88.5 plus minus 0.8 GeV. These are your theory numbers, okay. Now compare it with experimental numbers. These are pre-LEP, say for example. At LEP they became more precise. So MW at experiment essentially was 80.9 plus minus 1.3 GeV. MZ experiment 91.9 plus minus 1.7 GeV. Now you see, even at pre-LEP there is a huge difference between the theory and experiment. Okay, if you use the tree level values, you are falling way behind, okay, the experimental numbers essentially. So you cannot match your theory with experiment. So 1.7 and 1.3. The difference, yeah, that's coming because of sin square theta double. Right, that's the only thing which comes up. So you see, radiative corrections are super important, okay, to match with experiment, even at the pre-lep level. Yesterday I mentioned, last class we did a lot of things about lep, right, essentially, okay. So we'll continue doing that, but already we start having a lot of, just to give you a motivation for what is the situation. Why radiative corrections are important. Okay, so now you are happy that we should do radiative corrections, right? And why this is very important. Okay, now there are other examples also you can find in literature. Okay, I'll put up these notes, and if somebody latex these notes, some 3 books, okay, I'll give them a chocolate or something like that. Okay. Okay. Now, so let's start with the first parameter, which is the precision parameter. We'll come to left, forward backward symmetry. But the first parameter which I want to introduce is called the rho parameter. This is the first electroweak precision parameter which we are trying to introduce. Okay, so the rho parameter is defined as, at the tree level, how many of you heard about the rho parameter? Did you hear? Okay. Should know this is a very crucial important parameter which is measured very precisely. Okay, and if you want to extend any standard model even with a single another Higgs, it will create problem for this parameter. Okay, so at the tree level, what it tells you is that this parameter should be 1. Why this parameter is nothing but the ratio of mw square by mz square cos square. So what we write as mz square cos square theta w is equal to mw square, the tree level relationship. You take the ratio and call it as rho, nothing else. Okay. Okay. Tree level process, because we know this is the definition of mz square, right, essentially. Okay, but when it renormalize, mw goes by mw square plus delta mw square, mz square goes as mz square plus delta mz square essentially, and so the rho parameter will get modified, and now it is super precisely measured after lep up to 4 decimals. Okay, and that is the problem actually. So, but this is extremely sensitive because it's measured up to 4 decimals. Suppose if you have a 2 Higgs doublet model, this gets violated essentially, unless you align the 2 Higgs doublet model essentially. Yeah, still valid essentially. So this puts a very, very important constraint on any extension of the standard model. Most extensions by adding extra SU2 doublets or something like that. So now we had to compute the row parameter theory in the standard model, radiative corrections, shift this away from 1, and that is called delta rho. And delta rho is related to delta r. Okay, if you read my paper, I think we mentioned it in the 2 Higgs doublet paper essentially. So delta r is the sin square theta w modification. Okay, so this is called delta rho. So I'll just do a little bit of derivation of the pardon? Pardon? Oh yeah, it related to the t parameter. T parameter. I'll come to the Peskin Takeuchi also. Okay. This was supposed to be over in 2 lectures, but it's the 3rd lecture. I am not finished actually. But because I think this is very important, you should know something a little bit essentially. Okay. Okay. So the first thing we need relations between okay. Now there is a way of writing this thing. Okay. Okay. I think there are several definitions of this delta rho. I'll use one of them. So one of the crucial things is something called the so to calculate, before calculating delta rho, I'll just mention one thing essentially. So what are these the definitions of pi's and sigmas essentially? All the vacuum polarization graphs we'll keep seeing them hopefully by regularizations are essentially called pi. Now how many pi's are there? The one of the biggest thing which comes in the standard model is gamma z mixing. Okay, so you have pi's are gamma gamma, gamma zz, gamma ww, pi's, and then pi gamma z. So these are moment independent vacuum polarization graphs. So the vacuum polarization graphs are defined by this. So GC is there, no? Why GC is there? No, gluon doesn't mix with anything else. It's colored, right? Essentially, it cannot mix with anything. Okay, so these are all your regular diagrams. This is there in QED. This you can expect in your and a weak interaction. What is new is gamma Z interaction. So you have a diagram in which you can have gamma and Z. Now this will modify various things. This can modify your sin square theta W, it can modify everything. Now this single diagram, then you can also have self energy diagrams. Okay, you can also have self energy diagrams. Now these, all these pi's have q square dependence. Now you can measure them at whatever energy you want. At q square is equal to 0, the pi's are used to define known quantities like electric charge, GF or something essentially. And q square is equal to mz square, you can actually measure them essentially. It's a linear combination. Okay. So these are one things, and then there are the mass corrections. These are the self energy diagrams. So this is exactly like in QED, we sum over all the self energy diagrams. Okay. So self energy which are essentially called as sigmas. So whether it is W or Z. Okay. So a given diagram can have contributions also bosonic as well as bosonic are self energy diagrams, fermionic are essentially vacuum polarization diagrams. Okay. So you can also have bosonic contributions essentially. Okay. Now one is a mass correction. No, the process is the same. Right, there are corrections essentially. One, so what you want to do is you want to systemize the radiative correction systematically. So you want to renormalize quantities, you have to define into, so which corrections you want to absorb into which parameter, which corrections you want to absorb into which parameter. That has to be done systematically. Now you can do it in a completely different way. Okay, of course. Okay, but then it doesn't make sense because generally we want to do everything in a particular fashion essentially. So self energy, when you essentially mean only the bosonic contributions essentially. Okay. Okay, so in this case what happens is you start, so this is the geometric series which we always know. We have G mu by Q square. I know you can go through this notes for more details, but I am not going to do the full notes. So if you have a vector you have unlike photon, these have massive vectors. Okay, that's the main difference essentially. So you have this geometric series. This geometric series can be summed over, and then this gives you Ig mu by q square minus mv square minus plus sigma mu. So yeah, what is the mass of the vector? V is vector essentially. W or Z? Oh, you are right. Both should be in subscript. Okay, all of them are the same. Okay, right. Yeah, it is just geometric series. It's square 1 minus square and over. So after renormalization, the way you do renormalization is essentially mw square is equal to, or mw0 square is equal to mw square plus delta mw square, mg square 0 square is equal to mg square plus delta mg square. With this identification, you can define at the pole essentially at the q square is equal to mw square. Mw square is equal to real part of sigma w. I put in subscript or superscript at mw square. Delta mz square real part of sigma z at mz square. Now you put this back into this expression. Okay, you put this back into this expression, and you see that when q square becomes mz square, the denominator just becomes this relation. Okay, okay, you put it back into the propagator essentially. Okay, the renormalization condition, you put it back into the propagator, and you get these expressions. Okay, now I didn't tell you the entire procedure of renormalization, but I'm just telling you the final results, because if you want, you can look into it. RZ gauges, what are the Z, okay, everything essentially. It contains the quarks. Right. Now, but yeah, so that's how you define it. Now, what you do is, now you have to define, say, electric charge. Now, every part you have to define in, it will be a combination of pi pi gamma sigmas. Okay, electric charge will be a combination of both the things. Okay, so for example, if you want to do electric charge renormalization, whereas masses will only contain this one. So for example, what will end up having, you have for the rho parameter, all this is to introduce what is the correction to the rho parameter, essentially would be the sigma correction. I'll give you a say for example, electric charge renormalization, which you have done in QED, but in standard model. will contain okay. This entire piece is new in the standard model. Okay, so you want to scale, you want to make it dimensionless essentially, so that is the reason you put it by divided by mz square, and every charge and everything is defined at q square is equal to 0 essentially, like g minus 2 or anything like we do in QED essentially at q square is equal to 0. Okay, and these factors are correspondingly the mixing between gamma and c essentially. This sin theta w and cos theta w essentially. Now we won't do so the dominant degrees of freedom come from the bosonic degrees. Now if you look into the notes, I did several one loop diagrams calculations. You can do these calculations. I showed how to do them. So you can summarize this all these one loop diagrams in terms of Pasterno-Weltman functions. Okay, so the Pasterno-Weltman functions you can so there are this so you can use, you can redefine. I'll just, for completeness, I'll just mention what are these functions. So first you use dereg, so you can define them as 1-point integrals, 2-point integrals, and so on. So essentially, so this is the expression which Devjyoti likes very much. Okay, that's what he was asked several times in his compre. So q minus t for d k 2 pi d. So the one of the first is just if we have a single propagator. So that's called an A function. So it's called an A function. Now A is divergent. A is a divergent. Is this divergent or convergent? Then 2-point functions. These are called 1-point integrals. Then there is 2-point integrals. So 2-point integrals will come in diagrams like this. Okay, 1-point integrals will come in diagrams like this. Okay, 2-point integrals are defined all these are present in loop tools. Okay, in fine calc and everything nowadays. So 2-point defined, but you should know this, and there is a very nice book. If somebody is interested in one loop diagrams, I'll share them a Dropbox folder. Okay, which has very nice lecture notes on one loop integrals and everything. So one loop integrals are completely solvable. Okay, very systematically you can solve them. Simple partial fractions and everything you can use. Okay, except when the external momenta is non-zero. When the external momenta is 0, they are extremely simple to solve. Here all external momenta is 0 essentially. Okay, you can very easily to solve essentially. When the external momentum is non-zero, the corresponding functions are dilogarithms and sometimes called Spence functions. So which you can find in 2th paper essentially on time sheet. So 2 power d 1 by k square m1 square k plus q whole square m2 square, and this integral is defined by I take pi square function b0 k square m2. This is quadratically divergent. Okay, this everybody agrees, right? This if you do a cutoff, it just goes as lambda square essentially. As you go in higher and higher ones, they become less divergent essentially. So these log divergent essentially. Okay, and the C functions are essentially which come in penguins. Okay, so if you have penguin diagrams, something like this essentially, penguin diagrams, they are called C functions. And if you have boxes, you get D functions because there are 4 propagators essentially. Okay. Now in the notes I have done some simple calculations essentially for the vacuum polarization graph. So for this calculation of delta rho, you don't need penguins and boxes because they are not important essentially, but you can find, so boxes are completely so if you have, it's just a function, it's d power d k 2 pi by d, same 4 propagators with 4 masses, and you have d 0 q square m1 m2 m3 m4, same thing, c0 m1 m2. Then you can have c1s which have 1 momenta, okay, c2 c3 c4 so on so, okay, and d0 d1 d2 d3 so on so. So so the b's, you can dissociate this integral into 2 a's. Okay, you can do a partial fraction essentially. So whenever you have this is a very simple trick. So there are 2 partial fraction tricks you can use. Okay, if you have the same momenta essentially, so this will be just m1 square minus m2 square 1 by k m1 square k m2 square. Okay, so in that sense you end up having what is b0 b1 b2 and so on, so you can derive essentially, because if you have a k mu k nu, okay, you can add a momenta and this just becomes so for example 4 minus d integral d power 4d 2 pi d k mu by the same thing k square minus m1 square k square k plus q whole square minus m2 square I by 16 pi square b mu. This is what I was telling you, that you can add always a momenta in the numerator. This was good. Okay. Now you can define what is K1, okay, B1, and so on. So, and if you have 2 K mu K nu, you'll have B mu nu. Okay. Why it should be 0? Which one? Huh? K, in the which one? K goes to minus K. It's yeah, it goes, but right. If you have a single one, okay, it depends upon the external momentum, right? Essentially, there is a Q is sitting there essentially. Yeah, it's not completely a function of. So these are vector, then there is a tensor, and so on. So you can use partial fraction tricks, and say for example, I'll just give one more example, and then so then you define everything in terms of scalar. So the basic idea is that even if you have a tensor integral, you have to define everything. There is a very famous paper called Scalar One Loop Integrals by Tooth. You should all read that paper. Okay, 71 or something. Yeah. So I'll just finish this thing and I'll come to your question. So B mu is equal to K mu B1 of Q square M1 M2, and so B mu nu is equal to G mu nu B22 Q square M1 M2 plus Q mu Q nu B21 Q square M2. Yeah, somebody had a question. Yeah. Okay, so all this is based on the idea that whatever be your one loop integral, at the end of the day it could have a very terrible structure in the numerator, tensorial structure, but it always can be decomposed into scalar functions essentially. So you'll end up having only a bunch of scalar functions, either A functions, B functions, okay, and in the limit of external momenta going to 0, say for example if you are calculating G minus 2 or something essentially, so where you define external momenta going to 0, in that case they can all have simple analytical forms essentially. Okay, if you, I can give you references and various things, but if you are computing something which is very boosted, say for example, where you cannot say if you are computing a process in a collider in which you have a penguin or something, say for example if you are computing beam is on decaying radiatively to some gamma and some other thing, there in a collider you cannot set the mass of the external momenta of the B to be 0. So if you are doing in Bell experiment, say for example, and we have radiative decay of beam is on, okay, so the external momentum has to be taken into consideration, and so you cannot use external momentum is equal to 0, but still those functions can be solved. You can, they are given in terms of, you can decompose them into scalar one loop integrals, okay, and the external momenta range you have to fix. Instead of logs you only have dilogs, okay, and those are called Spence functions. And okay, I didn't bring my watch. Or what is the time now? 12:30. Okay. Okay. Say for example, all these processes are like this. You should remember that. Okay. Now, when you are differentiating something like an electric charge or something, okay, you can take them, the external momentum is equal to 0. But here, in addition to the loop momenta, there is already a Q sitting here essentially, which will be equivalent to say P1 plus P2 is the value of the propagator. So that is the external momentum. When it is zero, when you are computing, when you are defining electric charge. So when you are defining electric charge, you are not sitting at in a LEP experiment or something. You are sitting at atomic scale essentially. You are defining F1. It's an infinity, right? Essentially, as you know. Yeah. When you are defining electric charge or a coupling constant, essentially, you have to set it to be 1. So you say F1 of Q square goes to 0. Right? I put it in symbols so that you'll remember it. And the same symbols essentially. Okay? So you define it at Q square is equal to 0. The bare charge, or if you want to call it this. B1 is when you have one it's a vectorial integral and it's decomposed into a scalar part, and the scalar part of the vectorial integral is called B1. B2 2 and 2 1 are the scalar part of the tensorial integrals. Everything is scalar integrals. At the end of the day, the integrals are scalar. There are no vector integrals. Okay. So I think scalar 1 to I am forgetting. Passarino. I think these also NPB. Around 71 essentially. No, but all this is very nicely covered in this fat book of Wenzerl. Okay, there is a very nice book on Feynman integrals. Okay, by Stephen Wenzerl. It's very nice. Okay. Now this is all. Now he also talks about how to put it in computer and everything. Okay. So you can actually do all these self energies and vacuum polarization diagrams nicely using loop techniques. Okay, developed by Tooft and Weltman and Passarino and everybody. So the A function, just to give you the form, A function looks like something like this. And delta is equal to 2 by epsilon gamma I Euler law. And the B function B0, just to give you a picture, also has the delta So these all have the analytical form. This can be reduced into analytical form actually. This integral can be done into an analytical form and so on. So essentially, this has an analytical form. So using all these tricks, we can write gamma gamma is equal to electric charge renormalization. I just want to, I hope today I'll try to finish rho parameter. Yeah. Gamma gamma. These self energies are important. I am insisting on going through them in greater detail because I want to define STU parameters. Okay, these are extremely important essentially. So gamma gamma is equal to alpha by pi qf square fm k square. If there is one fermion going in the loop, of mass, so this is what it. So Q of the fermion, some or all fermions, of course, essentially. Okay, so this is the form it takes. And then you can actually calculate it for various cases. So what happens if there are light fermions? What happens if there is the charge of the fermion? Okay. Yeah. So minus 1 by 3 for down quarks, 2 by 3 for up quarks, and so on. Photon is massless. Okay, so pi gamma gamma k square sigma gamma gamma. The same thing. It's just a redundant definition essentially. Okay, there is no mass renormalization for the photon. Now you can, this vacuum polarization graph, now pi's, you can take the limit where masses are very large than when the momentum is k is much larger than m square, mass of the particles. Say for example, if you are sitting in LEP energies, then k is very large compared to m square. Okay, so in that case, except for the top quark, everything is has that limit, satisfies that limit at LEP energies. K square is much larger than m square essentially. Top quark is not produced at LEP because it's very massive. Okay, again remember the numbers of LEP. It starts with 100 GeV, 90 GeV or something, and it goes all the way up to 200 GeV. So it cannot produce, produce tops. Yeah, top is 175. For LEP physics, it's not produced in LEP. No, you can produce, it cannot be produced. E plus E minus going to FF bar. I will come to LEP physics again essentially. Okay. So for LEP physics, k square m square energies except top, this expression is easily done has a simpler form, alpha by 3 phi qf square delta minus log m square by mu square plus phi by 3 minus log k square by m square plus I pi theta of k. So except top, okay? Okay. Again, I repeat, we are self energies are important because we are looking at E plus E minus, and the mediator is always photon essentially, okay? Photon or a Z, and we are especially looking at photon Z mixing. Now the self energies can be evaluated at any momentum you want. At q square is equal to 0, they end up being definitions of either GF or electric charge or something, but q square is equal to mz square is the place where they have been measured, okay, where they have been measured essentially the corrections, okay, you can isolate these corrections. So that's the basic idea essentially. That's the reason why I'm trying to do the theory for it essentially, okay. Similarly, the opposite limit is also exist. I'm not writing it, you can see it in the notes essentially, you can see it in the notes. So I'll ask Saravana to get it xeroxed. There are 3 sets of books. It will take some time, okay. It will take a week or something, but he'll put it up essentially, okay. Now I'll just write photon Z mixing. Now this is important. Because it has a lot of physics in it. It really tells renormalization exists in world as well, okay. Okay. So this formula, now you can actually, this is just vector coupling. So whatever that means, QF you evaluate in the same fashion we did for by gamma gamma. Okay. Vector coupling means sin theta w or whatever comes into the picture essentially, okay, meaning the difference between the whatever comes here the Z coupling. Z coupling contains T3 minus that coupling, right, essentially that point. Now why it is physically very interesting, now you think it's all mathematical jugglery, right? Now what happens when k square is equal to 0? What should happen to this loop? It should be equal to 0. Yeah, excellent, that is the correct answer. Why? Because the Z doesn't play, the photon Z mixing will not play a role at low energies when you are defining the electric charge, okay. So the entire renormalization scheme really works. Gamma Z okay, Now what this does, now you can ask the question now, okay, what about sigma gamma z essentially, okay, there is also sigma of what about self energy is essentially self energy contribution. Pi gamma z also goes to 0, sigma gamma z also goes to 0, and everything essentially, okay. Pi gamma z and sigma gamma z are roughly nothing but different, they are not different. But what it does is, because of the z sitting here, it distinguishes between the up-type quarks and down-type quarks, up-type fermions and down-type fermions, and it fixes how much the splitting should be. Okay, so you cannot add any extra up-type and down-type. Okay, in particular, if you look at ZZ, the self energy of ZZ, okay. Similarly, you can have now ZZ pi's are nothing but this divided by mz square essentially, okay. So the vector coupling is defined as T3 for the fermion minus 2 charge of the fermion sine square theta w to SW CW, and the actual vector coupling is T3F to SW CW. Actual vector coupling comes with gamma 5. Vector coupling comes with gamma mu. This is gamma mu, gamma 5 essentially. So gamma z equal to alpha by pi sum over all fermions. Here F is equal to up plus and minus. So what is plus and minus? So the definition is, if there is nu E, this is M plus Q plus V plus A plus. Vector coupling, actual vector coupling, charge and the mass. Down type means M minus Q minus V minus A minus. So sum over all vector where we are in Z, right? We didn't do W yet. Okay, 1 second, I'll just finish this. So this formula contains alpha by pi sum over all Vf square plus AF square by 4SW square CW square 2B22 K square MF plus K square by 2 B0 K square MF minus A MF minus MF square 8 CW square SW square B0 K square MF. So this is gamma sigma ZZ. This is the formula essentially. So you can derive it, but now you see the up type and down type have different couplings, different masses here, and all this will enter in the loop function. All this will enter in the correction essentially. So different couplings, and so what is this measurement doing? It is telling you how much it is split. Okay, they should be split in such a way that the measurement should not be spoiled if you introduce anything. This will become, again you can do the same thing with W. So we did pi gamma gamma, pi gamma z, pi zz, now pi ww essentially, sigma ww. Now in the W case, only the W, in this case, in the Z case, both doublets and singlets contribute. In the W case, only the doublets contribute of the standard model. Okay. So for all this by ZZ, sigma ZZ. Okay. I'll just write formula for this thing, sigma W. Okay, much simpler. Again, you can take the limits. Now the W loop, M plus and M minus will come. They see the splitting between the up and down. Remember, the W loop will contain this is the up type quark and this is the down type quark, whereas the ZZ it will be the same type quark. Okay, minus A M plus A M minus by 2 plus K square minus M plus square minus M minus square by 2 B0 K square M plus M. So some loop function, but it's sensitive to the mass differences. Again, also you can take the limits and everything. Okay, and you can actually derive the formula what happens again like we do for the top quark essentially, for heavy fermions, I'll just write it for heavy fermions. This entire thing becomes it has also color factor 3, sigma z nc alpha by 3 pi v plus square plus a plus square. Minus 3 mt square yeah, we will do that. Okay, no, K square is not mt square. K square is much smaller than mt square. K square is much no, No, I didn't do this limit earlier. I did the opposite limit. MT square is much larger. K square is much larger than MF square we did. Now I am doing the opposite limit. Okay. Because I want to derive an analytical formula for delta rho essentially. For any k. For any k. For any k. Sorry, I think I should have mentioned it. I didn't take the limits essentially. Now I am taking the limits for heavy fermions with 3 colors explicitly mentioned. Okay. Plus means upside type and minus means downside fermions. Okay. Maybe you are lost. We did general formula for pi gamma gamma, pi gamma z, sigma gamma gamma, sigma ww, sigma zz. Okay, for any k. And then we did some limits for k square greater than mf square only for pi gamma gamma. And pi gamma z we also did the same. We didn't do that limit, but we just said pi gamma z goes to 0. In the limit k square goes to 0. Okay, up to that particular point we are done. Now I am introducing heavy fermion limit for gamma sigma zz and sigma ww. Yeah, essentially, because only the heavy fermion, only one fermion is heavy compared to the left energies. For a case, for the case k square is much less than mt square. Okay, you will realize why I am doing all this business. Okay, and then sigma w k square is equal to nc alpha by 3 pi k square by 4 sw square delta log mt square by mu square. Just give me 3 minutes essentially. I'll tell you why this is interesting. So what turns out is that I defined mw0 square is equal to mw square and so on, so right, essentially. In this notation, finally, when you can retain using putting all that into the definition of delta rho, it will just become sigma zz at 0. Delta rho at k square is equal to 0. We'll come to other parameters at k square non equal to 0 later on. That will come as STU parameters. Okay. So at k square is equal to 0, E is defined as this particular fashion. It will come to because these are all tree level masses. Mass is defined. Okay. Now k square is equal to 0. I can easily take only this term which is non-zero. The first term goes to 0. Okay. By putting the definition in the first definition of delta rho. Okay. Delta rho, I get this particular part, and this will give me delta rho is equal to this is the result. I can erase this, right? Essentially, yeah. But you can find it in the notes also, but you don't have to note it down. Okay. But all you have to see is the first term goes to 0. That's what I want. The first term goes to 0, only the top mass will remain. So the correction due to the top quark for delta rho in the standard model now you put in the model numbers into this. Okay, alpha is equal to 1 by 128 measured at lab. Sin square theta w is equal to 0.223 also measured at lab. Cos square theta w is equal to 0.77 measured at lab. This gives me delta rho is equal to 0.00859609. Okay. This is the definition, denomination. This is the definition of delta rho. Okay, in some words we can say it as definition. Now this matches with the experiment pretty well, essentially. So rho is equal to 1 plus 004 or something, essentially, which you can see, okay, in PDG or something. So within the standard model, this is dominated by rho parameter is dominated at 1.1% level by the top quark. So you see that this is precise up to 10 power minus 2. So roughly 0.1% level rho is measured. So what we saw today is that if you have just one single Higgs doublet and we renormalize the standard model and calculate the correction for the parameter rho, it should come out to be around 10 power minus 2, 10 power minus 3, 8 into 10 power minus 3. So it's roughly around 1%. Okay. Okay, 0.8% or if you want. So roughly around 1%. Okay, 1% is also a bit too much. Now if you have some extra Higgses and everything, they start breaking the rho parameter condition in the tree level itself. Okay, there are many cases in which the rho parameter is broken at the tree level. So for example, Randall-Sundram models or many other models essentially which break them at the tree level essentially. So okay, and also and we'll see meaning many of this anything which is strongly coupled is but simple things you think that strongly coupled will have very strong constraints because of the technical thing which we'll do it next class perhaps. I thought I'll finish it today, but this itself took a long time because I wanted to introduce one thing. Okay, it need not be strongly coupled, weakly coupled also theories like just adding a single extra Higgs doublet will create a problem for the rho parameter. In general, I'll give you this nice formula. For the rho parameter with n Higgs doublets, which is one of the assignment problems which you'll get. Okay. Right. K square much smaller than mt square. Other quarks you can forget it because top quark is so heavy. Okay, you take the limit when essentially top quark is the only source of the correction. Rest of the masses don't matter at all essentially. Yeah. So the rho parameter, if the Higgs doesn't get a wave, it doesn't contribute to the rho parameter because that wave will not contribute to the W and Z masses. If the extra Higgs doesn't get a wave, so it won't contribute to the W and Z masses. See, rho parameter is only sensitive to the W and Z mass ratio. So if you have an extra Higgs, which also has a wave, so that the moment it gets a wave, it contributes to the W and Z masses. So it will modify the ratio of W and Z. So in general, if we have n Higgses with Vi waves, okay, so then the general formula is T is the T1, T2, T3, you know, this the three SO2 generators essentially, okay. Okay, T into Ti plus 1, Y is the hypercharge, T is nothing but the T3 value, whether you are taking SO3 doublets or triplets or whatever essentially. So you can take SO2 doublets, you can take SO2 triplets, and in some models there are 4 plates also. Any idea which model has 4 plates? It's one of the first grand unification theory. Patib Salam. Okay, there you can put in, if you want, put in. Nowadays some composite models also have 4 plates essentially. Some dark matter models have 4 plates essentially. Yeah. So minimal dark matter models also have 4 plates. Okay, but they may not be fermions, they may not be scalars, but if they are scalars and they get a wave, they will modify the T parameter by this representation. So the larger the T value, okay, so this will, okay, so you can have triplets with Y is equal to 4 or Y is equal to, or definition of Y depends upon it, or triplet or doublets with half. So as long as the numerator cancels such a way that it gives you the correct value, okay, of the standard model, the representations are highly constrained. You cannot add any Higgs representation and give it a wave and say I get it W and Z boson masses from it. Okay, so this is the one of the biggest constraints, and we will see this is another version of this is the T parameter. This will also play a role for anything which splits the masses. If you have extra fermions, so if you want to put an extra fermion, why there is no 4th generation? Okay, if the 4th generation contributes and the splitting is very large, okay, it will spoil the rho parameter. Okay. Pardon, effective? Pardon, effective? That is there, but it also spoils the n is equal to 3 experimental limit. Okay. Both are, yeah, both are around 2.99 or something essentially. But you can principle you can avoid the left limit on the 3 generations by saying that the 4th generation is heavier than 45 GeV. Okay, but then it leads to a lot of problems. One of them is from electroweak friction test. Other is the coil coupling itself should be very, very large. If it's a chiral thing, it should be top quark coil coupling is 1. So if you have a 4th generation, it should be heavier than top quark and everything. So its coil coupling will be much, much larger than 1. Okay, so that is a problem. You cannot do perturbation theory with it. Okay, so all these issues are there. It also spoils, yeah. But yeah, MSSM actually is a decoupling theory. It's a very, very nice theory. Okay,